All right, let's try this again. Okay. So yeah, so anyway, it's section 14, derivatives, calculus. And we're going to focus on gradient descent and derivatives today. So hopefully some of the stuff you've seen before. And I think I mentioned before I cut out was that mod 2 is kind of like a focus between like the mathematics, and we're going a little more deep with the mathematics as well as some of like the programming parts, for example, like HTML, APIs, and stuff like that. So just kind of know that we're kind of spreading, we're kind of learning a little bit of everything going on here. So, but know that the derivatives is going to be really useful when we go into machine learning. And this is because it's one strategy for us to basically develop our model. So you guys all did like linear regression so far, and you actually find out, I believe we're going to talk about it next section, but one issue with linear regression is that if you try solving linear regression, what's it called, like in its full form, which you can do, you can solve like a system of equations like linear regression. The problem is that computationally, just to kind of give you some numbers, it goes up by n squared. So if you have twice as many things to predict off of, so you have like twice as many features, it takes 4 times as long for the computer to do it. And then that keeps going up. So if you have like, 10 times as many features, it'll take you 100 times as long. So realistically is that we won't be able to do a full linear regression in its closed form. So we use strategies like gradient descent to basically do this prediction to basically find the line of best fit. And we'll talk about this a little bit in a second. But the first thing we need to do in order to do any of that stuff is actually know what derivative is. So I think you guys probably had experience with the derivatives before, like you probably had some experience with calculus, right? And so just kind of, some of this might be just refresher. Some of it might be like like a long time ago since you've done it. Other times you might say, oh yeah, I remember this pretty well. So just kind of be aware that we're going to talk about a few things. So the first thing you should know about a derivative, and this is how I always think of derivatives. Derivatives, we talk about rates of change. I just think of it, a derivative is a slope, because I know what slopes are. Slopes are easy on a line, right? Basically, how steep is a line? And that's really what a derivative is. It's basically saying how steep is this change, okay? And that's what rates of change. So the rate of change for a linear function is literally the slope. So again, a linear function is just literally a line, right? So if we have our graph like this, we have our line, that's my best line I can do, is that our slope is literally the derivative. So if you remember back how to find slope back in like grade school, you would do the change in y, this is the y-axis, right? Okay, and the change in x divided by the change of x, okay? Or if you remember like rise over run, okay? So this should be like really review, right? Like, oh yeah, I know how to do that. So again, just to kind of review is that when we say about rise over run, you probably have seen this triangle 1,000 times. Basically, how much you changed went from here to here. That is your change in y. And then going from here to here is your change in x. Okay, pretty simple. And of course,
That's good drawing, man.
what's that, great drawing?
It's good.
Oh, you're gonna see a lot more drawings today too. So yeah, can you guys see that okay though? Yeah. All right, cool. But our slope on this line here is going to be consistent, right? Basically, it's just the same steepness. And that is literally what our derivative. So we'll usually note our derivative f prime, right? You'll see derivatives written in different forms too, but usually a quick way is just f prime of x, right? And just know, you probably saw this back when you did even like the interview to get into the program. Yeah, you guys are doing some nods right now. Hopefully that wasn't too bad of an experience. But basically you can think of it as like, oh, you start off with an x, you say the change in x, the change, and say start from here. So this is just the y value, and this is just the x value right here, okay? So pretty simple for a linear function, but everything in a sense when we do a derivative is we just assume it's a linear function, and we take the limit to basically close in as small as possible to get to that exact derivative. So kind of going off of that, I'm going to draw some more pictures here. So rate of change of a nonlinear function. It's the same thing, but the derivative is basically going to be as small as possible. So I'll kind of show you, oops, that's not what I want to show you. Here we go. So if we have a nonlinear function, so here's my axes, okay? And we have something like, let's say like a parabola, okay? Parabolas are easy, and it kind of continues onward. Okay, I won't draw little arrows because you don't need that. So if I have this function right here, this parabola, and we wanted to find the derivative of this point right here, well, an estimate for that point could be like, well, let's just go ahead and draw a line from here to some other point on the function right here, okay? And you could find the slope of this point. Obviously, you'll notice that that's probably not the best idea, like, because what would happen is like we would find the slope of this fire. It's like, oh, it's pretty flat, but you can tell in reality when we draw out the slope on the parabola itself, you can see it's like, well, it's pretty steep right here, right? If you drop the ball, it would go down pretty quickly. So obviously not a good estimate. But what we can do is we can try to improve it by saying, well, let's move the point closer. So we'll say, well, instead of from this point to this point, let's draw it from this point to this point right here. And of course, I can't do straight lines. Straight enough, okay? And you can see it's like, okay, that slope is closer to like that exact point. And of course, we can move it a little bit closer. Like, well, let's go ahead and move it even closer, going from this point to right there. You're like, okay, that's closer now. And then if I can zoom in a little bit more, you can see like, okay, like the blue is kind of like that perfect slope. And basically what it comes down to is that we move this point closer and closer and closer to the exact point that we're interested in. And that becomes our exact derivative, our instantaneous rate of change, okay? Fun words that you'll hear like a lot of times when people talk about derivatives. But all we're essentially doing is making the limit. You can think of it a few ways, but you can think of it like the limit of the change in x, which is from here to here. So you can think of like this is our change in x. We're making that change in x approach 0. And that gives us a derivative. The other way you can think of it too is saying, okay, limit of, if we call this like x2, and this is like x1 right here. We can say, oh, the limit of x1, x1 approaching x2. That's equivalent, right? Basically, because the change in x is just x2 minus x1. So you can see, oh, the change in x would approach 0 if x1 becomes very close to x2. All right? Sound good? All right. So hopefully that feels pretty review, right? Easy stuff. And of course, what's nice is that if you have any kind of function, whether it's a parabola or whatever you want, right? If I have some funky looking function, okay? If I had some weird function like this, I can find a derivative at any given point, but basically just doing that same, what's it called? That same closing in on the limit, right? So easy stuff. Hopefully it feels pretty easy. Okay, so again, rate of change, that's just a derivative, okay? So this comes down to the basic rules for a derivative, right? And so again, this is a lot of stuff that's actually in the curriculum right now that I'm kind of going through, so kind of go through it, but I figured just to do a quick review. So the first thing, the rule is the power rule, which should feel, I mean, I think that's like the very first way you learn a derivative. Let me clear this out. There we go, okay. So power rule, if I have x to the power of 5, okay, if we take, or I should, let's start off with x to the power of 2, okay? You guys probably know this. What's if I took the derivative with respect to x to this, what would be this derivative? Does anyone know?
X to the 1.
So x to the 1, and then there's actually a factor in front of it too.
Oh, 2, yeah.
Okay, cool. Yeah. So yeah, that's your derivative right here. And if I had similarly, like if you already know the pattern, x to the power of 3, what would this derivative be?
3x squared.
Yeah. Cool. 3x squared. Cool. I saw you guys. It's funny. You guys all unmuted yourself at the same time. Right. So 3x squared, right? So pretty simple. Basically, it comes down to x to the power of n. So, and this could be an integer. This could also be just like a fraction even. You basically just say, okay, it's n, whatever that number was there, times x to n minus 1. Okay. Pretty straightforward. This even works for like n equals 0 because and x to the power of 0, does anyone know what x to the power of 0 is? Like what kind of number that is? Just 1, right? Yeah, a constant. And so if we have that number, we have x to the power of 0 minus 1, well, we have 1 over x. But then of course we can just say, oh, well, n was 0. So the derivative of a constant number is 0. So just know that any number, okay, that derivative, it's just 0. Okay, and so that's the mathematical part. This is probably like what you've learned a lot. One thing you might not have like really had a focus on is saying, well, okay, cool, like that's what the derivative is, but like what does that actually mean? And so, can I zoom this out? Oh, there we go. Okay, getting faster. Okay, so one way you can kind of think of it is like, well, if you start off with, let's say, x to the power of 2, well, that's a parabola, right? Okay. I don't know why I always end up drawing those little arrows when I draw these little parabolas. But you can imagine the slope if I moved, like say, okay, what's the slope right here? Well, the slope's kind of pretty steep. And then over here, oh, that's not so steep. As you get closer, it's like, oh, that's even like almost flat. Down here, it's exactly flat, right? And then you go up again and then up again, right? So it's like, oh, a negative slope, a negative derivative. So like, imagine like a -5 derivative, right? And then it's like, okay, it's -4 derivative, -3. These are all made up numbers. Okay, this is like a 0 derivative, there's like a 2 derivative, a 4 derivative, and so on. Okay, so you can kind of imagine like, oh, that's the slope, that's the slope is changing, right? Changing from negative to positive. Well, if I were to graph out what the slope looks like, the derivative for each point, okay, let's say, oh, you start off with a very small value, so like negative, and it goes up and up and up and up. And so down here is like, okay, where it was like, let's say, it's like, let's say this is the value of like 2. At that point 2, this is -5, okay? And basically what it happens if you graph this out, it's like, oh, you end up just getting a straight line. The slope, the derivative changes at a constant rate. Basically, as you move across the x-axis on y, you basically have the slope change in this linear fashion. So if you look at this, this is our x squared value. This ends up being something like x. Basically, it's a line, okay? So this is actually where this kind of comes from. It's like, oh, okay, like this is where essentially you have that derivative. You're saying like, okay, let me go see how the slope changes. And that's what this line right here describes. So you can kind of see similar. It's like, okay, well, we have a slope like this for a line, or like we have our line, and our derivative is just the slope, okay? The slope never changes. The slope is constant. So if we drew out this graph, well, it's just a straight line, just like that, right? Okay. And then if we had a constant function, basically it's like, okay, y equals like 3. Okay, and we have this y equals 3 like this. This is just a straight line. What's the slope of this straight line, this horizontal line?
It would be 0, no slope.
There's no slope. It's not steep, right? It's 0. So that's the same idea here, is that if we have a constant function, the derivative of that is 0. So that's all a derivative is. You're saying, hey, what's the graph of this slope? And if we had a weird function that, you know, went like this, basically it's like, well, how does that slope change? And basically we can take a derivative mathematically and get that exact function. But essentially that's all we're doing. We're just plotting out the points. There's a great, I'll kind of refer you guys. There is a great YouTube channel series called 3 Blue, 1 Brown. So it's like 3 blue, 1 brown. He has a whole thing about like linear algebra, derivatives and stuff like that. But he does a great visualization of trying to like understand a derivative and understand like what these things are. He even talks about some machine learning aspects too. Highly recommend if you have some extra time just to kind of watch those videos. They're pretty great. They're kind of long, you know, video wise, like for YouTube, like 15 to like 30 minutes long. But they're all very engaging and they're all pretty looking. So cool thing to watch. And I think in a former life, he was a data scientist, but now he's more of an educator. So something to keep in mind. Cool. So that's derivatives. Hopefully that's all quick review. That's the power rule, which is the most thing, okay? And then we can do things like additional terms and coefficients. So basically this comes down to the fact that if I have, I'll go through this really quickly. I have x to the power of 5, and I have something like 3 times x to the power of 5, and I would take the derivative of this. So I'll write this as like, I wrote this too far off the side. There we go. Okay. F of x. And then I do like f prime of x, which is the derivative. All you do is say, okay, you just keep that same constant, in this case 3, times whatever the derivative of x to the power of 5 was, which was 5 x to the power of 5. That ends up being 15 x to the power of 5. Okay. So hopefully that's pretty familiar. So basically it just comes down to if you have a coefficient in front, if you have some value in front, you can essentially you could just keep that outside and then multiply it by your actual derivative because it's a constant, okay? Another thing is that if you have, like, let's say this is a function f of x, and it's equal to like 2x squared plus, I don't know, 5x. All you do basically is take the derivative of just this guy, take the derivative of this guy, and just add it together. So f prime of x would then equal 4x plus, in this case, just 5, since the derivative of 5x is just 5, okay? So this way you can get, basically every time you have addition like this, you can essentially just add all the terms together. You can take the derivative of each individual term and then put them all together, okay?
Wouldn't 15x to the fifth be 15x to the fourth?
I'm sorry, say it again? Oh, sorry. You're talking about this guy, right?
Yeah.
Yeah. Oh, that's my mistake. Yes, you're absolutely right. Yeah, this should have been dropped one power. Okay. But yeah, same like the concept's there is that you say, okay, the coefficient in front multiplied whatever the derivative of this guy is, and if you do the derivative right, you'll have 5x to the power 4. Okay, and then of course 15x to the power 4. Cool. Any questions about this? Pretty straightforward. One kind of trick one, just so you know, if I have 1 over x to the power of 2, like this, so it's a fraction. Let's say like 9. Okay, so this is my f of x. What would be the derivative f prime of x? So I'll tell you first, like, okay, we just have the 9 in front. Okay, and then what would be the derivative part? Does anyone have an idea?
2? Well, 2x.
So just 2x like this?
2x.
1 like this? Okay, yeah. So this is like, wait, what am I supposed to do, right? So this is when, like, this is supposed to lead into like the chain rule, but if you're a cheater like me, not cheater, but like take some shortcuts, because I say be lazy like a fox, don't work too hard. You can rewrite this and say, well, okay, that's cool, there's a fraction there, but let's just do 9 times x to the power of -2, because negative powers basically become fractions. So if this is x to the power of -2, then all I got to do is say, okay, for our derivative now, f prime of x, we have 9 times the derivative of x to the -2. So how do we do the derivative? Well, we take this power right here, we do a multiply, times, right, whatever the derivative of, oh, we drop 1 power. So -2 minus 1 is just x to the -3. So that's a derivative right there. Basically, I rewrite this guy as a negative power, and once I have the negative power, I just follow the same, subtract 1 off. So -2 minus 1, I'll have a -3 power, and then just take whatever exponent was there, -2, multiply in the front. So then simplifying this a little bit, I get -18 times x to the -3, or if I wanted to write in fractional form, it'd be -18 divided by x to the power of 3. Okay, make sense? All right, cool. Again, it's a pretty simple rule. Basically, just if you have coefficients, you just multiply them after you do the derivative. If you have multiple terms like this guy right here, you just take the derivative of each term and then add them together. Or if it's a subtract, basically you sum them together. You basically take the derivative separately. And then things like if there's a power, you just do the power rule. Powers are super easy. You can teach like 6th graders to do this kind of stuff if you really wanted to. They probably wouldn't understand what's going on, but that you could tell them what to do. So cool. So that's that part. And the next part basically ends up being the chain rule, which I'm going to go through it really quickly just because I don't think it's super necessary for us to kind of like really harp on like, what is the chain rule and stuff like this. But just know that you can combine parts where if you have something like, let's see here. We'll do something that's really simple first. So we'll do like, I'm doing y. 5 of x, or f of x is equal to, let's say, x to the power of 2. And then let's just say we take this whole thing to the power of 3. Okay, so if you know the mathematics, you know that this will simplify to x to the power of 6, which means if I take the derivative, you know that this should be 6x to the power of 5, right? So we know that's what the answer should be, okay? But with the chain rule, you can say, well, let's say, I don't know why you would do this, but like in this specific instance, just going to show an example, we could say, okay, this is like a function within a function. And what I mean by that is like this f of x is really like saying, okay, we're taking some function h of x, okay, and then applying it to some other function g of x. And so in this case, we can think of like g of, I'll write it off to, I'm trying to find a good space. Okay, if I have something like this right here, you can imagine, okay, g of x will give x squared, okay? And h of x, whatever I put into h, it'll output to the power of 3, x to the power of 3. So if I combine these together, if I say, okay, apply g of x first, I get x squared, and then apply h of x, I get to the power of 3, and I get this guy right here. So this allows me, if I can write my function down like this, okay, because remember I just got this guy, but if I can write my function like a function of a function, I can use something called the chain rule. And the chain rule basically just says, okay, if you have a function of a function like this, you can take the derivative in a special way. So what this ends up happening is like, okay, you say, what is x? I'm trying to think of the best way to approach this. So you can kind of think it's like, okay, this is at h prime, so the derivative of h of g of x times the derivative of g of x. So this is going from here to here, okay? And so what this will look like, because remember, for this specific example, x squared, x to the power of 3, we should get, this should be our derivative right here. So let's try to apply this. So we saw that, let's start with g of x, because g of x is pretty easy. So g of x, as we saw, is just x squared. So g prime of x, so you see this like x squared, g prime of x would be 2x, right? So if I go forward, this part will be 2x. And I'll just write it like multiplied, okay? And then if I do h prime, well, h of x, that function, was just saying x to the power of 3. So our derivative, I just said h prime of x, what would be the derivative of this guy right here? So I have x to the power of 3.
3x squared.
3x squared, good. Thank you. Okay, so you have 3x squared here. Okay, and so it's like, okay, whatever we put in into h, we would get this out. So whatever we put into h prime, okay, the derivative of h, we get 3 times whatever you put in squared. So this would simplify to say, okay, h prime of x, or sorry, h prime of g of x, that would say, okay, what you're gonna do is do 3 times g of x squared, right? Okay, and so what was g of x? Well, g of x was just x squared. So we go 3 x squared squared, which in that case just simplifies to 3 x to the power of 4. But we still have this multiplied by 2x part, and that ends up being 6 x to the power of 4 times x, which is just 6x to the power of 5. Okay, so you can see we got the same exact answer as before. And this right here, going from here to this function here, is the chain rule. Okay, so does that make sense? Just that the fact that we have this ability right here. And just know the chain rule seems like, I think sometimes people take it as like the chain rule is like this really big thing, but all it comes down to is like, well, you just need to figure out what the functions are. Like if you can apply a function within a function, then you do the chain rule. And to be perfectly honest, like if I ever do the chain rule, I always say like, can I simplify it first? If I have something like this and I can simplify it to a power rule, I'll do that first because I'll get the same answer. But sometimes if you have something like this where you have a derivative or like you were trying to do the mathematics on this is how you would think of the chain rule right here. So again, this is just applying derivatives. Curriculum goes through a lot more detail, so I'm not going to harp on it too much. But any questions on this guy? No? Okay, cool. And then last part, which, let's see here. The last part of this derivative section is finding the minimum and maximum with derivatives. So the way this is probably the more important part when we actually get into gradient descent, because gradient descent will actually say, hey, we're trying to find what is the minimum and maximum, or what is the minimum value for a certain function. And that's the whole point of gradient descent. So when we actually find a derivative, the reason why one of the important parts of using a derivative is if we have a function like this, okay, we want to find where is the minimum value. And the way I kind of like to imagine this is that if I took like some ball and put it on the function, where will that ball like go land in? So if I drop this ball on this like slope, the ball will eventually roll down and eventually like might go over here, and kind of like oscillate and then finally end up at the minimum point. Okay. So you can kind of think of that. And that's true for any kind of weird looking function, right? So if I have a function that looks like this, if I had a ball that went here, you can imagine the ball goes down, maybe kind of some momentum goes up a little bit, goes down a little bit, goes down, and eventually settles right here. So essentially what happens, like you can kind of imagine is that the ball's trying to find this lowest point, okay? And the way it finds this lowest point is through finding a slope. If it's really steep, if it's steep like this, it's gonna fall downward. It's gonna go down towards wherever the downward part is, basically towards the slope. So what happens is that, well, in order to find the minimum point, what we can do instead is say, hey, let's just find where the slope is 0. Where is it flat? Where is it gonna land in? So you can imagine, like, if it didn't have momentum, this could also land in these parts right here, okay, where it's flat. Well, flat just means a derivative of 0, right? Right here, there is no slope. There isn't any slope here. There isn't any slope here. There isn't any slope here. That means the derivative is just 0. So we can say, hey, where are the points where it's flat? And that basically says, all right, if this is our function, f of x, okay? What that means, like, oh, if we say, hey, where is that derivative equal to 0? So what x's make this true? Basically say, when is the derivative of 0? So once you find this part, so for example, you find derivatives like, okay, the derivative is like some weird function like x to the power of 4 minus 3x squared. Okay, so that's the derivative. Okay, I don't really care about how I got it. It's like, this is the derivative. Well, okay, if I set this equal to 0 now, all I do now is like solve for x and say, okay, when this is true, solve for x, and those are my points. In this case, I can just factor it out to x squared to x squared minus 3. So if I do the math real quick, basically x, and set this to 0, x can be 0, can be positive or negative square root of 3. Okay, so these are just like, if I did the math to figure out like, oh, what parts of x make this 0, I'd find, oh, hey, that means when x is at 0, so let's say this is at 0, when x equals 0, and when x equals negative or positive 3 or square root of 3, and then x equals negative square root of 3. Okay, that's what it's saying. It's like, okay, these are the flat points. Now here's the issue, is that if I had a graph that looks like this, sorry, I'm trying to draw up. If I have a graph that looks like, goes up like this and then down, okay, maybe that's not the best thing. Let's undo that. Let's say we have something that goes like positive like this and then down. Okay, this is my minimum. I want to find this minimum right here, but notice that the derivative right here is 0, but the top here, the derivative is also 0. So if I just say, hey, f prime of x is equal to 0, it'll give me this point and this point. Okay, so the way we can say, hey, okay, I want to, these are my candidates, these are my minimum maximum, but I want to find which is the actual minimum, I can actually do a second derivative. And that second derivative now will allow me to say, hey, when I take that second derivative, so I do like basically derivative of the derivative. Sometimes it's like two dashes like that of x, okay? And say, hey, I put whatever values here, I'll call it like, xc. So these critical values, that's how I usually see the notation. Say, okay, for f double prime of c, I can say this number will either be positive or negative, or it could even be something, it could be 0. And if it's 0, it's an inflection point, which means it basically is neither a minimum or maximum. It's kind of like this point would be an inflection point. Okay, but basically say, hey, is it positive or negative? And this will basically tell me if it's going to be, these terms are concave up or concave down. Basically, it's like if this is greater than 0, that means it's a minimum. Okay, and if it's less than 0, that means it's a maximum. Okay, so this allows you to basically very quickly say, hey, put my first derivative, get my critical values. Once I have my critical values, find the second derivative, plug my critical values in that second derivative. Is it positive or negative? Okay, and if it's positive, you see you have a minimum value. Okay, so that's the process that's going through to find the minimum and maximum value. Okay, any questions on what that meant, what that looks like? Cool. Thumbs up, thumbs down. Okay, cool. And just to quickly iterate, just to kind of like, it's really simple steps. All it is like, all right, if you wanted to find let's say I wanted to find minimum value, which is what it's going to be for gradient descent. All you do, you start off with f of x, right? Step number 1, f prime of x is equal to 0. Okay. And that will give you value, that will give you solutions when you solve for it. And those are xc's. Second step, take the second derivative, so find the second derivative, plug in x of c, and then ask yourself, is it greater than 0 or less than 0 when you plug in those values? Okay, and then once you have that, you know if it's a minimum or maximum. Okay, cool. So that's all the derivative stuff I'm going to talk about for this guy right here. Okay, I'm trying to see what time it is. Ooh, it's kind of late. I guess we got messed up a little bit. Sorry, yeah, so that's all for derivatives on here. But now I'm going to talk about gradient descent. So for gradient descent, this is where, oops, why do I have this guy in here? Okay, for gradient descent, I'm debating about how much I should talk to you guys about it because we only have about 10 more minutes. But I'll give you guys the overall, like what the motivation is. Maybe we could talk about it a little bit on Friday then. But the motivation for gradient descent is, like I said, is that you try to do a linear regression. In linear regression, you can find the exact value, but it turns out that it's not the most efficient way. So it's like, well, can we find a better way? Maybe not get the exact value, but get close enough. And this is where basically we have something where we use something called a cost function. Okay, and our cost function for linear regression is just going to be the residuals, or RSS, right? Residual sum of squares. So it's something we calculated way back in, section 10, I think, maybe section 11 even. No, I think it's section 10 or section 9. But we're basically finding the RSS, and that's going to be something called our cost function. And this basically tells us that how good is our model, right? How good is the specific model? Okay, so I'm going to go ahead and run just all of these guys to kind of show you. So the way you can kind of imagine this, like we kind of been using packages to automatically find this line of best fit. So I just created some random numbers right here. Okay, so 300 random numbers, and you can see these little dots right here. And I said, okay, our regression formula will look like y equals mx plus b, or in this case, I'll just put it as b plus ax, right? Because we can have multiple values. But for a single 2D line, basically all you have to do is like, hey, b plus a times x, right? And so I can say, well, let me just guess, okay? Let me just guess what these values are, okay? And see how well that line fits. So in this case, I looked at this line right here and I put in values for b to be 1, a to be 10, and you're like, oh, not the best thing. So you can see it's not exactly right. So what value could we change a to b to make it closer to fit on this line?
50.
50, good. Let's try 50, okay? And you see, oh, yeah, that's pretty good, right? Not bad. So you can see, hey, it's pretty good right here, right? You can see it's got almost the exact slope going on right here, but maybe not exactly right. It's maybe, for example, when you shift it up, so maybe we can adjust B now. It's like, okay, well, let's go ahead and adjust B to I don't know, 2. Okay, you see, hey, that's pretty good. So we moved it up a little bit. Kind of playing off here, you actually got pretty lucky there, Eric. But if I had like 100, let's say like you said, okay, let's try 100, or let's say, remember that really lowest point, we said 100. Like, okay, cool. It's like, oh, overshot. It's like, well, halfway between that, it's like, well, let's say 60. Okay, and you try that, and you're like, not quite, right? Let me try like 40. Okay, you say, too overshot it again. And basically you can kind of keep playing it back and forth and get 50. And 50 works out pretty well, but maybe there's something a little bit better. Maybe it's like 50.3 or 50.2 or something like that, right? There might be a way to figure out, something that works out here. If you, again, like this is essentially like lucky. Now, I don't know if this is the reason why you chose 50. If you're paying attention, I use this right here to generate some random data. This is actually where the data is generated from. So you can actually see if a 350 would actually be right on there. If I change this to, let's say, 40, okay, and then I run this guy again, you can see that's our 40, okay? So basically I'm generating that random data on here. But if you didn't know this part right here, okay, you could guess. I know, that's pretty good. Okay. So yeah, and if you're not lucky, you'd have to figure it out a little bit, go back and forth. And so you can kind of like adjust your model, but you obviously don't want to just guess randomly. You want to do better and better each time. And so we can actually use the error values. So do you remember how we actually determine the error for a regression line? Like what are the things that, like what do we do? Just describing it in words.
It's calculating each point's distance from the regression line.
Perfect, right? This is our regression line right here. Thank you, Josh. And basically it's to say how far are each of these points from the regression line. And we take that distance, and if we do a squared sums, we actually square it, right? We say, okay, whatever this distance is, let's square it. So you can imagine it basically making these big old squares and then adding up all of those errors and basically say how big is that square value. You also could have done the absolute value with like an L1 norm versus an L2 norm, but we tend to do squared because squared will punish very big values. So we can use that RSS. That's essentially what RSS is. So RSS is our residual sum of squares. Okay, we can do that to find, and that's what this error function is right here. Okay, we can basically say, hey, what's the difference between these points right here? And then we say, okay, let's square those errors. Okay, so basically make those squares. And let's go ahead and sum all of them up. And that will be our total error. Okay, and we can use that value then and say, okay, and let's say we just kind of kept making different lines. So we like made a line, let's say we tried this line. We weren't as lucky as Eric. We tried this line here, 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 this line here, and so on, right? And we basically see, okay, how well do each of these do? And if we do that, we would actually get like something like this, where you see, oh, really bad error over here, depending on what our slope was. So you can see like 40 was pretty bad. And then we get better and better and better. 50 is pretty good. And you can see here in this case, oh, 52 actually ended up being pretty good right here, very low error, and then bigger error again. So you can actually see it's like, hey, this is actually where we want to be. We want to be at this point. So actually, if I go ahead and run this too, since we have some new data, since we used 40, you can see it's a little bit different in this case. So you can see this is our minimum right here. We want that minimum amount of error. And this is where gradient descent is really useful. Remember, I just said minimum, right? And we just talked about derivatives, not a coincidence. We can use derivatives to basically find that minimum point right here. And that leads us into gradient descent.